Hello, this is Charlene. We're going to be talking about solving exponential and log functions in this video. We need to remember a few things. This base to an exponent equal to some expression is our exponential form, and our log base to some expression of some expression is equal to the exponent. That is our log form. And we need to remember that we can toggle between the two. We can go from exponential to log or from log to exponential. And sometimes in solving these functions, we need to toggle between the two. We also have our log rules that we need to remember. Our log rules, the product rule, the quotient rule, and the power rule, they allow us to either condense or expand our log expressions. And we also are going to be touching a little bit on this idea of the natural log. Now, the natural log always has a base of e. So it'd be like if it's the letter E, which stands for a number, it's like 2.71, blah, 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 blah. It's a naturally occurring number in our universe and in nature. But if it's the number E raised to an exponent is equal to some expression, so it can be toggled back to this version. But the thing is, though, there's a time when we can use natural logs, but the same rules that apply to all of these log rules, the same rules apply to natural log. The only difference is that the base is always going to be the naturally occurring number E. Okay, let's kind of scroll down and see what we got going on down here. Okay, so it says solve each of the equations for problems 9 through 12, state the exact solution and the approximate solution rounded to the nearest hundredth if needed, and be sure to check your answers and exclude invalid solutions. So this part right here, excluding invalid solutions, if we have a log and let's say that we had x plus 3. But let's say that we found an answer for x that was x is equal to negative 5. Well, if we plug that in, log of negative 5 plus 3, well, that means that that is log of negative 5 plus 3 is a negative 2. Well, that is a big no-no. That's a big no-no. So we cannot have this answer. This answer would be rejected if it caused this to be the log of a negative number. So we would reject that. So we need to just keep that in our back of our mind because we may have to test solutions. Okay, so let me go ahead and erase this. But before we start this first problem, I want us to think about something right here. I have written over here 3 squared is equal to 3 to the 5 minus 3. Well, if it tells us that these are equal, if they are truly equal, then that means that these exponents should be equal to each other. And of course, if I subtract 5 minus 3, well, 3 squared is equal to 3 squared. So that is a true statement. But the concept that I want you to remember is that if this base of 3 and this base of 3 are the same base, then that means that their exponents are going to be equal to each other. We can set them equal to each other in order to solve for a variable that may exist in those exponents. So having said that, let's go over here and look at our problem they've given us. Okay, so they've given us 2 raised to the power of the expression 3x plus 7 is equal to 1/4. Okay, so right now, this has a base of 2. So if there's any way that I could get this other side to also have a base of 2 over here to some power, then we could actually solve by setting this exponent equal to this exponent. So that's going to be our challenge, is to try to change this 4 into an exponent or to a base of 2. So let's think about what we can do to the 4 or the 1/4. Let's just think about the 1/4. So I'm going to go ahead and bring that down to raised to the 3x plus 7 expression. and that is equal to 4, 1/4. Can I rewrite 4, 1/4 as 4 to the negative 1? Can I write that? Yes, I can. So the thing is, though, I'm one step closer to making this 4 look like this 2. So there's a 4 as a base, there's a 2 as a base, but can I rewrite 4 as a base of 2 with a power? It's like 2 to what power would give me 4? Well, 2 squared would give me 4. So that means that I can rewrite this. Okay, so 2 to the 3x plus 7 is equal to 2 squared, but I still have that negative 1 out there. So now do I have a base of 2 and a base of 2? Yes, I do. And that means that now I can actually set this exponent equal to this exponent and solve for my x right here. There's my x. Okay, so we're going to do that now. We're going to say 3x plus 7 is equal to 2 times negative 1 is a negative 2. And I am going to subtract 7 from both sides, cancel those out. 3x is equal to negative 9, and then divide out the 3, and these 3's will cancel. And that leaves me with x equal to negative 3. So that is the solution for my x variable. Our next problem says 4 raised to the x plus 6 power, and it's equal to 3. And of course, this right here, this is an exponential form. This is not a log form. It's exponential. But like the first one, we tried to get the same base and the same base. We had in the problem we just worked on, we had a 2 and a 1/4, and we were able to get it to 2 and 4, and then finally to 2 and 2 as far as bases go. But this one right here, this is a 4 and a 3. Am I ever going to be able to get that 4 to turn into a 3 or that 3 to turn into a 4? No, there's literally no way, not without involving fractions or decimals or something weird like that. So we are going to do something different. Remember, I mentioned to you about the natural logs. This is where we're going to employ the natural logs because we cannot make these bases the same. We are going to take the natural log of both sides. We're going to say the natural log of 4 to the x plus 6 is equal to the natural log of 3. Now, what we should understand is that the natural log of 3, if you put that in your calculator, it's just a number. It's a value. It might be a decimal, possibly, but it's just going to be a number. But this right here, this has the natural log of 4. Now, this part is a number, but this exponent kind of complicates things. But if you remember our log rules, this is when we need to employ our log rules because this is an exponent. And our log rule says, it's a power. So our power rule on the log rules says that if I have a power, I can bring it down in front. So that expression is in the power position, and I am allowed to bring it down in front, which is kind of exciting, don't you think? So we're going to do that. We're going to bring it down in front. So this is what it looks like when I bring it down in front. And so now I have x plus 6, the expression, times the natural log of 4 is equal to the natural log of 3. And like I said, this natural log of 4 is just a number, and this natural log of 3 is just a number. So guess what that means? That means that I can actually divide out that natural log of 4, because my goal is eventually is to get that x all by itself. So just like order of operations always wants us to try to isolate our variable, we are going to try to get rid of everything we can except for the variable. So we are going to divide out the natural log of the 4. And that's going to allow us to cancel the natural log of 4 on this side. And again, natural log of 3 divided by natural log of 4 will just give us a number at some point. But let's keep working it out. Where do we end up at that point? We end up with x plus 6 is equal to that value. And of course, if you remember just algebra 1, how do I get rid of that 6? Well, I can subtract that 6 from both sides. And if I subtract it from that side, I also have to subtract it from this side. And then that will leave me with this right here. It's like this. It turns into this. X is equal to the natural log of 3 divided by the natural log of 4 minus 6. And all of this is just a value. So we're going to put it in our handy dandy calculator. And when we do, we're going to put it in our calculator, and it's going to give me this value, negative 5.207. And if I round that to hundredths, that would be equal to negative 5.21. So that is the answer for my x value. And of course, I can test it. If I go ahead and put that into my calculator as well, it's like 4 to the negative 5.21 plus 6. And let's see what it equals. So let's grab our calculator. We're going to do 4 raised to the negative 5.21. Actually, I'm going to grab some extra of those decimal places. So I'm going to put 2075, put some extras, because the more decimal places you put in there, the more accurate it's going to be. So negative 5.2075, and then plus my 6. So plus 6. And that gives me 3.0 with a really, really small decimal. But what did it tell me? It said that it was supposed to be equal to 3, so it checks out. That is a correct answer. That is an excellent choice for the value of x. Our next problem says that we have log base 5 of x plus 5 minus log base 5 of x minus 3 is equal to 4. So this has a subtraction. So that means that we are going to be able to utilize our log rules. When we have a subtraction, we are allowed to change our subtraction back into a quotient, and it is going to help us to condense this, but then we will be able to continue solving this. Okay, so we're going to rewrite that as this right here. So basically, I took this argument, that's what we call that expression. I always call it like an expression, but it's also called the argument. But it can be a single letter, single variable. It can be an expression. So the argument can be a number of things. But anyway, we took this argument, and this argument, this one went into the numerator, and this one went into the denominator. So I need for us to now recognize what that is. Okay, so let's think back and what does it look like? Does it look like the log form? It's like we have a log to a base of an argument is equal to an exponent. Log of base of an expression or argument is equal to an exponent. So this means that this right here, this is the log, and it is equal to the exponent. But I really can't do anything to that in its current state. So what we are going to do, we are going to convert this log base form into the exponential form. We're going to turn it into our exponential form. And let's make that a little bit bigger. There we go. So that's what we're going to do. We're going to turn it into the base to an exponent is equal to our expression or our argument. And when we do that, it's going to look like this. So again, there was my base, and now my base is in this position. So base is in this position, and then I have my exponent. My exponent was over here. Exponent was over here. Now my exponent is here. Now my exponent is here, and my argument. It's like all of this was my expression, my argument. It originally was here. When I change it to the exponential version, it moves to the other side. So it moved to the other side of the equal sign. So now this is my exponential form. Now let's look at it. Is there anything that I can easily do, just like normal algebra, math, or anything? Yes, I can go ahead and just do this little math operation. 5 to the power of 4. I can calculate that. So let's go do that and see what happens. Okay, so I end up here. 5 to the 4th ends up being 625 is equal to this expression. Well, it's looking more and more like something that we can solve just using order of operations. So let's go ahead and think about what we can do. Let's see. Let's make some of this smaller so we got a little bit more room. And we are going to try to get rid of that denominator. That denominator is not very handy. So if I multiply both sides by this expression, that means I could cancel that out. So let's do that. Let's multiply both sides by the expression x minus 3. And that allows me to cancel out x minus 3, and now I have the x minus 3 times 625 on this side. So now, using order of operations, I'm going to distribute that 625 into the parentheses. Well, when I do that, it looks like this. So I've now distributed, and I end up with 625x minus 875. 875 is what 3 times 3, 625 was. And of course, over here, I just was left with the x plus 5. So that's what I have, x plus 5. So again, my goal is to solve for x. So that means I want to get all the x's on one side, get all the constants on the other side. And so I can do that. Let's go ahead and I'll go ahead and leave it down there. Okay, so if I get rid of the x's, they cancel right there, but it's subtracted from the 625, and then add the 875 to both sides. And so that is going to give me, this is right here, what I end up with. I end up with 624x is equal to 1880. And then, of course, that's pretty simple, right? We just divide out the 624 on both sides, 624. And what is that going to give me? That is going to give me, that's what that was. And then here we go. Calculate on your handy dandy calculator, and you get a value of x equal to 3.0128. And of course, if I wanted to, I could reduce that to 2 decimal places, so 3.01. But I want to test this for a second. So let's get our handy dandy calculator and see if we can see if it actually makes sense, because all of this should it be equal to 4. Okay, so I'm pulling up the calculator, and if you notice, I am not using my rounded 3.01. I'm using 3.0128 because the more decimals I use, the more accurate my answer will be. So log base 5, or 3.0128 plus 5 minus log base 5, or 3.0128 minus 3. Is it minus 3? Yes, it's minus 3. Okay, and so when I put that in, I do get an answer of 4.00099, but it's a very, very, very small decimal. And of course, that proves that this is a good answer. 3.01, well, technically, all these decimals are more accurate, but they do give me a value of 4 in the end. Our next and last problem for this video says we have log of 3 plus x plus log of x minus 3 is equal to log of 7. Again, we have a sum here. And if we have a sum, that means that we should be able to use the product rule. If we have a sum, we can turn it back into a product. So let's go ahead and see what that looks like when I do that. Okay, so this was a sum originally, so now it says that I can take this and multiply it times this, and that becomes a product. So right there is 3 plus x, right there is x minus 3, and now they are being multiplied. They are in a product. Okay, so I need you to recognize what's going on here. And just as an aside, if we have no base, it's automatically a 10. We have a base 10 system, so that is the default base. So log base 10. So all those are log base 10, log base 10. But we need to recognize this. We need to recognize that I have log of something is equal to log of something. And particularly, it's log base 10 of something and log base 10 of something. And it could be any log. It could be log base 3 and log base 3. But if I do have that, the same log, let's see, here's the same log and the same log, then that means that these two arguments will be equal to each other. So this means that we are using the one-to-one property to rewrite the equation without the logs, without the logarithms. And here's what that rule looks like in your textbook. If I have the same log, log base b is on one side of the equal sign and log base b is on the other side, then these two arguments, the m and the n, will be equal to each other. The m will be equal to the n. So that means that all of this and all of that will be equal to each other. So let's go ahead and set those equal to each other. And now it's really starting to look like just some algebra. So if you also want to recognize the fact that this looks like two factors, that could possibly turn, if we multiply them back together, it could turn them back into a polynomial, probably a quadratic. Yeah, I think it'd be a quadratic. So when we do that, I'm going to multiply those together. And this is, okay, so it's definitely starting to look like a quadratic. There's an x squared term. And now if I just combine all of my like terms, it now is going to end up like this because let's see, we've had 3x and negative 3x canceled each other out. And then we brought the negative 7 over here, negative 7, and that gave us the 16. So we end up with x squared minus 16. Well, our goal is to solve, right? Is to solve for this x and solve for this x. So we still have an x. We still want to solve for it. But now it looks like what? It looks like a difference of two squares, which means that we can factor this according to a pattern in order to solve for the x. So it is a difference of two squares, and we can factor the difference of two squares like this, x plus 4 and x minus 4. So those are our factors, right? And then we can do our zero product rule. And then that will give us our solution. So the zero product rule says that we're going to do x plus 4 is equal to 0 and x minus 4 is equal to 0. And then when we solve it, it means that x is going to be equal to negative 4 and 4. And that is the solution for our final problem. Negative 4 and 4 should make this true. The only thing we want to check for is just to make sure that none of these logs become negative if we put the 4 and negative 4 in there. So if I put a 4 in here, it'd be 3 plus 4 is 7. Well, that's a positive number. And then if I do the negative 4, 3 plus negative 4, now that's a problem. Does everybody see that? It's like the x minus equal to negative 4. If I put that in there, 3 plus a negative 4 And you can't read that because that is too thick, isn't it? La, 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 la. Make it skinnier here. Okay, so if I do 3 plus a negative 4, that is going to turn into log of a negative 1. Well, that is a big no-no. So guess what? That means that we have to reject this answer, and our only valid answer is going to be the x equal to 4. Because 3 plus 4 is 7, and also if we put the 4 over here, 4 minus 3 still gives me a positive 1. So the only valid answer is the x is equal to 4. Okay, hopefully that helps you um, understand a little bit about solving for the variable when you're dealing with logs and exponential functions. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.